by Joachim Brod on dramatic effective theories. Joachim, floor is yours. Huh?
Okay, Marco.
Okay.
You were breaking up a lot.
Do
you still hear me?
Yes, I do.
Okay, good. You were breaking up a lot, so I hope the internet connection holds. And I think I understood that it should start now. Is that correct?
Say it again.
I think I understood that I should start now.
Yes. Yes, that's
okay,
important.
Good. Okay, excellent. Yeah, so if you, for some reason, can't hear me anymore, shout. And I hope the shouting gets through.
Okay.
All right. Well, welcome back to the lecture on dark matter effective theory. So today is the second part, and we will just continue where we stopped last time. And I think the best thing is to just recapitulate a little bit what we did last time so we get back into the flow. So the general idea of the lecture is that I want to show you how to calculate a scattering cross-section of a dark matter particle on an atomic nucleus, essentially with very general assumptions about the dark matter interactions. And what we started with last time is we just wrote down a very simple model, just a C-prime model, so an exchange of a heavy vector particle, simple Lagrangian, and then we just naively started calculating and just wanted to see where the problems lie and how far we can get. And we saw that we can actually calculate the cross-section. Okay, so I've written the cross-section here, that's the result. And in order to arrive at this result, we made essentially 3 approximations. So first of all, from kinematic considerations, we saw that the momentum transfer is very small. This is essentially limited by the velocity distribution of the dark matter particles in the galactic halo. So the momentum transfer and also the deposited energy is very small. And so and in particular, we assume that the mediator particle is much heavier than this momentum transfer. So we could expand the propagator, and essentially we ended up with a local interaction. So that's kind of this 1 over mv. V is the vector particle mass to the power 4. That is essentially, and there's no further momentum dependence. That's essentially this approximation. The other approximation is that the speed of dark matter in the halo is much, much less than the speed of light. It's about 1 per mil. So we can treat dark matter as non-relativistic. Okay, so the next thing that we did is we just used the leading approximation for the solutions to the Dirac equations. So the non-relativistic spinors, essentially the Pauli spinors. Okay, and the effect of this was that for this vector interaction, there was no spin dependence. All the spin dependence dropped out, and we just had a local contact interaction. Okay, one consequence of this, together with our third approximation, was that the dark matter is scattering coherently on all the nucleons in the nucleus. Yeah, and that was the third point. So we are scattering on a complicated non-perturbative bound state object that consists of quarks and gluons in a complicated way. But in these low energies, we don't resolve all this. Okay, and in order to calculate this, the cross-section, we could actually use a trick. We used an exact symmetry that is related to baryon number conservation. And we saw that essentially at very low energies, the dark matter just sees the baryons in the nucleus, essentially the numbers of protons and neutrons. Okay, so these are the 3 approximations that allowed us to actually get an exact result in this simple case. And then what we want to do next, and what we started already last time, is we want to generalize these approximations to a very general case. So we don't assume a vector mediator, but we assume just a general type of mediator. It could be a vector particle with vector couplings, or a spin 1 particle with vector couplings, or axial vector couplings. It could be a scalar particle that has scalar couplings, pseudoscalar couplings. It might violate CP, whatever. There are lots of different possibilities. And what we discussed is that at low energies, or let's say, if these mediator particles are heavier than the momentum transfer in general, then we can always approximate these interactions by contact interactions, by doing the same expansion of the propagator. And then we can just write down all possible possibilities for these interactions, and we just give them names, and we call them local operators, and they get numbers in a certain way. It's just a convention, and I'm just sticking to the numbers in the literature that I cite. So, for example, our C primed exchange at low energies leads to this vector-vector interaction that I called Q1, Q6. And 6 is the number of dimensions. So these are non-renormalizable operators. They're suppressed by inverse powers of the mediator mass. Okay, so this, in our case, it was, so the interaction was suppressed by 1 over m squared, so the cross section is down by 1 over m to the 4. And then I didn't write down all the different possibilities, but another one that I wrote down is an exchange of a scalar particle with pseudoscalar couplings, and I called it Q8Q, is its name. And it has these gamma 5 interactions, pseudoscalar interactions. And I wrote it down because we will discuss this in a bit more detail, and we will see that this actually leads to more complicated interactions that depend on the spin of the dark matter and of the nucleus. And it also depends on the momentum transfer. So that's kind of a non-trivial example. So I chose the simplest one for the start, and then we will discuss what about the more complex interactions. So that was kind of step 1 of the approximations. Then the next step is the non-relativistic limit, and we started discussing this for the dark matter. And the idea here is that, so we said that the momentum transfer is small, but if we think in terms of relativistic fields, then the 4 momentum has always the energy component in it, and the energy component is completely dominated by the mass of the dark matter. But if we are in the non-relativistic regime, the masses never change, they always stay the same. So the mass of dark matter, the mass of the nucleons and so on, they never change. So it makes sense to scale them out and get rid of them and just keep the residual momentum, or you can think of the momentum transfer. So that's one thing that we wanted to do. And the other thing is we want to neglect antiparticles. So in the relativistic formulation, we have the Dirac force spinors, which contain the particles and the antiparticles, but we want to just project out the particle components because the energy is not enough to produce any antiparticles. So just to make everything simpler, we want to get rid of antiparticles. So we split the general momentum into this large mass piece and the residual momentum. And then we rescaled the field by this exponential factor that, as we will see, gets rid of this large mass piece. And then we split the field also into components that are called small chi and capital chi. And the small chi will contain the particle components, and the capital chi will contain the antiparticle components. And this is done in a covariant way by introducing these projection operators 1 plus v slash and 1 minus v slash over 2. And I should point out I had then a typo in the lecture notes, and I think also in my lectures last time, the definition of the gamma matrices was kind of a bit screwed up, so I used the correct version.
Could I ask you a quick question about this part?
Vanish. All right, and the last thing.
Okay.
Yes.
Oh, thank you. So for this piece where we're neglecting the antiparticles, are we doing that because we're making some assumption about the matter-antimatter asymmetry, or is it just a field redefinition to make things simpler?
Yeah, so that's just a field. Okay, in some sense, we just drop pieces that we don't need. So it has nothing to do with the matter-antimatter symmetry. Just we want to, we say dark matter is a particle as opposed to an antiparticle with just convention. But we know once we say it's a particle, we will never in this scattering produce an antiparticle because the energy is by far not enough. So we just don't need these degrees of freedom. So we just want to drop them to simplify the expressions.
Okay, thank you.
Okay, sure. so the last thing that we did last time was we took the relativistic Dirac equation and we multiplied it on the left by this projector, and then we did some algebraic or some manipulations, and we found an expression for the anti-particle components in terms of the particle components. We could express the capital chi field in terms of a differential operator acting on the small chi field. That's where we stopped. And let me ask if there are any further questions about what we discussed last time. No, seems not to be the case. So then let us continue. So what we want to do is we just take this expression and we plug it into our original field. So this is the full relativistic chi field, which we split in this.
Recording stopped.
Joachim, I don't know if you can hear us. We can see you through the other screen, but you disappeared. Can you hear us? Can you hear us? I'm not sure. I see you typing, but I don't hear you. I don't know if you're. His video. Actually, he's connected with two devices, and
Can you hear me?
yes, now we can again. Yes.
Can you hear me now?
Yes. But now you're frozen. On the other hand, on your other device.
Okay. Okay, sorry about that. I don't know what happened.
Let's try to move on. Please restart.
Recording in progress.
Okay, I'll just continue. All right. Okay. Sorry about that. I don't know what happened. So I assume you hear me, so I'll just continue. So what we want to do next is we want to substitute this expression for the capital chi field into the relativistic field. And so what we get is an expression for chi, and that is just I d slash perp divided by I v dot d plus 2m chi plus 1 acting on the small chi d field. Okay, and we can now taking the non-relativistic limit now just means we take all our relativistic Lagrangian and we substitute for the relativistic field, we substitute this expression, which is just in terms of the particle components with the heavy mass scaled out. And I think there's this exponential factor missing. Should also write this, e to the minus I m chi v dot x. Okay, and you should think about this like these inverse derivatives. You should think of this as a Taylor series essentially. So you should write 1 over I v dot d plus 2m chi equals 1 over 2m chi, and then a series that starts with 1 and then higher terms that we will usually neglect. I v dot d divided by 2m chi plus and so on. And since these derivatives, these deltas, so they correspond to momenta, And these momenta are now all small because we factored out their mass. So you see that these higher terms are suppressed by powers of momentum of a dark matter mass. So they're usually, if dark matter is not too light, we assume that it's heavier than about a GeV or 2, then these terms are small and we can neglect them usually. Okay, and then we get the non-relativistic dark matter Lagrangian, or as it's called, the heavy dark matter effective theory Lagrangian. That's just the relativistic Lagrangian expressed in terms of these fields. So it looks like, so the leading term, the kinetic term, is just this one, bar chi I v dot d acting on chi. So you see there's no mass term, the mass has been scaled out. And then there are these higher terms that are indicated by a dot. And then there's the interaction term that we called L chi, and now I call it L chi v, by which I mean we substitute this non-relativistic field everywhere. Okay. I leave it to you as an exercise to derive this leading term in the free Lagrangian. It's a nice exercise, and as usual, the solution is in the lecture notes. But what I want to discuss is the interaction terms. And I want to discuss, first of all, the interaction that we had before, so the vector current, and see what happens if we substitute this non-relativistic field. So we write, let me start a new page. We write chi bar gamma mu chi, and then we substitute our expression, so that gives chi bar v e to the I m chi v dot x gamma mu e to the minus I chi m chi v dot x chi v. Okay, and in order to calculate this, remember that this chi v, first of all, this chi bar is chi dagger and then gamma 0, and this chi bar, it had a projector inside, this 1 plus v slash over 2. So what we need is, we need to calculate the following. Because of the dagger, what is implicitly written here is 1 plus v slash dagger over 2, then gamma 0, that's this gamma 0 here, and then gamma mu, that's this one from the interaction, and then there's another 1 plus v slash over 2 from the projector on this field. Okay, and you all remember that v mu dagger equals gamma 0, gamma mu, gamma 0. So we can write this as gamma 0, 1 plus v slash gamma mu 1 plus v slash. And now we commute this one past this gamma matrix, so we get a minus sign here, and we pick up a term from the commutator. So that gives gamma 0, 1 plus v slash over 2. Then one term is 1 minus v slash over 2, and then a term from the commutator, which is just v mu, if you calculate it. And then you see this 1 plus v slash, 1 minus v slash, that's 0. We saw this before, so all that remains is just gamma 0 v mu, and then this projector. And this projector, again, acts on this field, and it gives just 1, because this field has already a projector inside. Okay, so with this small calculation, we see that this is just chi bar v, v mu, chi v. Okay, and if we are in the lab frame, or approximately in the lab frame, remember v0 is just 1, 0, 0, 0. So again, as we saw in our explicit calculation, only the 0 component contributes. So mu equals 0 contributes, the rest is 0, no spin dependence. And that's again just a contact interaction, as we found before. Okay, so that's very nice. So we reproduce our previous result with this general formalism. Okay, any questions? Okay, good. So now let's look at the somewhat more difficult example. which is the pseudoscalar interactions. If we do the same calculation, but now instead of a gamma mu, we put the gamma 5 interaction here, then we see, because the gamma 5 anti-commutes with all gamma matrices, we will actually, if we do the same calculation, but here we put the gamma 5 instead, then we will only pick up this term, and there will be no finite term from the commutation, because this just anti-commutes. So what you see is, in this case, the leading term just vanishes. Okay, so let me write this down at least. So for the gamma 5, we have 1 plus v slash dagger half times gamma 5 times gamma 0, 1 plus v slash equals 0, which means we need to keep the higher contributions in this expansion in this case. Okay, so need higher contributions. So we go to the next order and we write chi bar I gamma 5 chi equals, so now we keep the first non-trivial term in this expansion, and it looks like the following: 1 minus I d slash acting on you still hear me?
Yes, you.
Okay.
We stopped hearing you, but now it's okay. No, I see that you're talking, but
okay.
I don't hear you.
Okay. Okay, so we just include the one more term in this expansion. There's the exponential factor.
Could I ask a quick question, if you can hear us? I don't think he's talking.
Okay, so what we just saw is that the leading term vanishes. So
I think he just heard me. I can just hold on. Can you hear us?
yes, there was a question.
Oh, yes, thank you. Could you repeat, please, why we need to keep the higher order corrections for the pseudoscalar case?
I can hear you, yes.
Yeah, so that he heard me.
Yes, I can. Yes, exactly. The reason is just that the leading contribution vanishes. Like if you don't include these terms, then just if you take this current I gamma 5 and you calculate the leading term, because of the projectors, essentially this gamma 5 anti-commutes with this projector, so you get something like 1 plus v slash gamma 5 equals gamma 5 1 minus v slash, and this hits the other projector and gives 0. So the term that has just a 1 here vanishes.
Okay,
Whereas the
thank
next
you.
leading terms have okay. So the next leading terms have additional gamma matrices, and they will give a non-trivial contribution. And you see they come with derivatives. So these additional contribution will be momentum suppressed. And you can write this as, you just evaluate these derivatives, and then this term looks like d mu acting on chi bar v gamma mu perp gamma 5 over 2 chi v plus higher terms. And this expression in brackets you can show, and that's kind of a tedious calculation, so I don't want to show it here, but it's an exercise if you want, or you can look up the solution. This is just the generalization of the relativistic generalization of the spin operator. Okay, so this is just d mu divided by m chi, chi bar v, and then the spin operator of the dark matter. Plus dot, dot, dot. Dot, dot, dot means terms that are even more suppressed, and we drop them. Okay. Okay, and that's the general strategy. Okay, so whatever interaction you have, you insert this, our definition of the field, the expression for the field, and then you just calculate the leading contribution. And sometimes the leading contribution is a contact interaction, for example, for the vector field. Sometimes the leading contribution is a spin-dependent interaction. Sometimes it's a spin-dependent and momentum-suppressed interaction. It just depends on what you start with. Okay, so for an axial vector current, it's just spin-dependent. For this pseudoscalar exchange, it's spin-dependent and momentum-suppressed. Okay, so that's kind of the general strategy. Okay. Any questions here?
Yes, one.
Okay, there's a question.
Hello. Just a question about checking higher orders, because I mean you got 0, which is why you expanded out one term to check whether you get higher order stuff. So suppose you get non-zero for the first term. I mean, how do you develop an intuition to how many orders you must expand until? Because how do you know that the high order guys don't like collaborate and like cancel?
Well, I think I would say you just have to calculate it, but in the end, there are not so many different interactions. I mean, there are vector currents, axial vector currents, scalar currents, pseudoscalar currents. So it's just a few possibilities, and one can just calculate all of them, and then you just see what comes out. So, like for a vector current and a scalar current, the leading piece is momentum independent and spin independent. And for the pseudoscalar, we just saw it's momentum dependent and spin dependent. And then you can just go through the different possibilities and see what comes out. I don't know if there's a better intuition that you can have, but it's just a handful of possibilities that you can just check explicitly.
Oh, okay. Thank you. Actually, random question. Do you expand by hand or do you use Mathematica? Just random. Okay.
Sorry, could you repeat the question? I didn't hear.
I'm an experimentalist. I'm just really curious whether theorists do this by hand or they use like Mathematica or something.
So I will mention this later. So all these calculations, they have been done and they're implemented in computer code. So you never have to do these calculations.
Okay, thank you.
I will discuss this later.
Thank you so much.
I will discuss this. Yeah, sure. Yeah. So kind of, in some sense, this is just giving you the background, like what goes into the code. So you understand what's going on, but there's no need to do these calculations once they have been done. Okay. So that kind of finishes the discussion of the non-relativistic limit for the dark matter currents that we assume to be elementary. And now the third approximation that we did was, or the third problem we had to deal with was the hadronic current, so the currents of the quark and gluon fields in the nucleus. And again, also here we want to go to the non-relativistic limit, so to the low energy approximation, but there's an additional complication because at low energies, there are no quark fields and there are no gluon fields, but at low energies, there are instead nucleons, like bound states of quarks and gluons, nucleons, protons, neutrons, nuclei, and pions. So we have to kind of deal with both at the same time. And like, let's say generally, what we are interested in is a matrix element that looks something like this. So there's some nuclear state on the outside, and then, for example, for our quark vector current, it looks something like this. And that's kind of a non-perturbative object, but you can use symmetries because the strong interaction satisfies symmetries like parity conservation and of course Lorentz invariance and so on. And you can show that you can describe this this current in terms of just two functions that depend only on the momentum transfer. Okay, so these are so-called form factors. So you can write this as some external nucleon spinner, and then a function that depends on the quark flavor and the type of, let's call it this n for nucleon, for simplicity, on the type of nucleon. It depends only on q squared, comes with the gamma mu, and then there's a second one, I over 2m nucleon, another function, and another structure. So q is the momentum transfer. Okay, so you can always parameterize these matrix element like this, and then in principle you could measure these functions. So you can do scattering experiments, for example, not with dark matter, but with, I don't know, electrons or other particles that we have, and you can try to measure these functions and just map them out experimentally. But that's kind of not always possible. I mean, for the vector currents you can do it. For other currents it might not be feasible. For example, for scalar currents or pseudoscalar currents, because we don't even really have an elementary pseudoscalar. So the question is, do we have a more systematic approach to get these hadronic matrix elements? And what we want to do is, again, we want to use a symmetry, now not an exact symmetry like baryon number conservation, but an approximate symmetry of Qcd, which is called the chiral symmetry. Okay, and this allows us again to do an approximate expansion of these currents. Okay, so what we want to do is use the chiral symmetry of Qcd. Okay, and maybe some of you have heard this before, but if let's start with the Qcd Lagrangian, and let's just look at the terms with the quark fields. So the Qcd Lagrangian looks something like this: q bar, then I d slash q, and d slash is just the covariant derivative of Qcd. So it has the kinetic term and the gluon interaction to quarks, and we can split the quark fields into left and right-handed fields, and then write it like this: q bar left I d slash q left plus q bar right I d slash q right. Okay, and this d mu is just d mu plus I strong coupling times the gluon fields. Okay, and the important observation is that I should say what Q is. So Q is just the collection of light quarks. So it's the up quark, the down quark, and the strange quark. And this Lagrangian is invariant if you rotate these quarks into each other. So if in other words, if these quarks, if you neglect their masses, so these quarks are all very light compared to a nucleon, let's say. So you cannot distinguish them from each other. So you can just rotate them into each other, and this Lagrangian doesn't change. And you can rotate the left and the right-handed components independently of each other, and nothing changes. And that's called the chiral symmetry. In mathematical terms, it's SU3 left cross SU3 right. Because you can just do a unitary rotation on these left and right-handed components and independently. Okay, if you haven't seen this, then it's a good exercise to try to do this explicitly. The symmetry is not exact because we know that these light quarks have small masses. So the symmetry is approximate, but it's a relatively good symmetry. It's good enough for our purposes, say. So now at low energies, we don't have quarks. So the degrees of freedom are not quarks, but there are other particles, and among them are pions. And what we can do is we can just write down another Lagrangian in terms of pion fields instead of quark fields that has the same symmetry. And now there's one complication. This symmetry is spontaneously broken. And for a spontaneously broken symmetry, there are Goldstone bosons. So for each generator of the symmetry that is broken, there's a massless or light degree of freedom, which is called a Goldstone boson. And there's just a way of writing the Qcd Lagrangian in terms of these Goldstone bosons. Okay, and I will not explain how this works because this would be far too complicated for this short time, but I just give you the results. And one way to write this Lagrangian is to define a matrix of pions, or if we have up, down, and strange, it has pions and kaons and eta fields in it. So pi over square root 2 plus an eta field, eta over square root 6, pi plus, k plus, pi minus. You just have a 3 by 3 matrix with all the pion fields in it. And then you take this matrix and you exponentiate it. So you write u equals the exponential of this matrix. So exponential with some scale factors I times square root 2 times pi over f. So that's a kind of very complicated expression for these fields. But that's the ingredient that you need to write down the Lagrangian. And this f you can identify by calculating let's say a kaon decay from this Lagrangian. You can, or pion decay, you can identify with the pion decay constant. So that's a parameter that you can measure, and it has the value of about 92 MeV. So that's kind of experimentally determined. And you see that's actually the only parameter that appears in this parameterization.
I have a quick question.
Yes.
I think I got a little bit lost in the math here. Is all we're doing right now calculating the standard model piece of our scattering propagator?
Well, what I'm trying to not even explain to you, but just show to you is how can I write a Lagrangian that is equivalent to the Qcd Lagrangian in terms of quark fields, but using pion fields instead. And then we will say that these two Lagrangians give the same physics in some sense, and then we will use the pion Lagrangian instead of the quark Lagrangian in order to calculate the scattering. Does that make sense?
Yes, and is the purpose of doing that just it's going to make the math simpler in the end? Is there some physics reason to do that?
Yeah, the physics reason is that this scattering process happens at very low energy, where you don't see any quarks. If you want to see really quarks in scattering processes, you have to go to a high energy collider, let's say the LHC. At the LHC, it makes sense to talk of quarks because you destroy protons into their constituents and you see jets and so on. But here, this is all super non-relativistic. So the dark matter will never see a quark. It will just see the nucleus. It might see a pion, that's why we need pions, but it doesn't see quarks. So we need to somehow express the physics in terms of the physical degrees of freedom that are relevant at the energy scales of, of the physics that we are trying to describe.
Okay, so in our initial calculation, we did this by assuming baryon number conservation, and now we're kind of going a step further, but still looking in the low energy limit.
Right. So the initial, so our initial calculation was I just chose in such a way that it's super easy, because you can show. I mean, this will come out of the general formalism later, but you can just show that the dark matter just sees the whole nucleus. Okay. Essentially, what we showed in this initial calculation is that dark matter sees a point nucleus. And if you want, you can include the form factor for the whole nucleus. So if the dark matter has enough momentum, it can see there's a distribution of protons and neutrons, but it will never see quarks. It will just see the protons and neutrons as a whole bunch in some sense. And that was kind of easy to see because we had baryon number conservation. For more complicated interactions, it's not that easy, but the idea is the same. We want to just write down what the dark matter actually sees. Just imagine you're a dark matter particle. What do you see? You don't see quarks and gluons. You see just a nucleus approaching. And you might see the spin of the nucleus, or you might see just the nucleus as a whole. Or you might see a pion that is emitted by the nucleus. That's what can also happen. These are essentially the possibilities.
Okay, that makes sense. Thank you.
Sure. Sorry, it's very vague because I don't want to get too much into technical details, but I hope kind of the physics picture comes across. So these are just all very low energy processes.
Can I ask another question?
Absolutely.
Well, it's a very basic question, but why do we know these chiral symmetries spontaneously broken at low energies?
Why do we know? Well, essentially, maybe the reason that we know is the following, that we know for each, if you have a symmetry of a Lagrangian, but it's spontaneously broken, so it means it's not realized in the ground state of the theory, then there's a theorem by Goldstone that for each such broken symmetry, there's a massless particle, which is called a Goldstone boson. And now in QCD, what we see experimentally, that there are nucleons that have masses of order GeV. And then there are also other particles that are much, much lighter, which would be kind of a mystery, where do these particles come from? But we can understand these are actually the Goldstone bosons, and these are the pions and the kaons. And they're not exactly massless because the original symmetry is not exactly exact. So they have small masses because the quarks have small masses, but they have masses that are so these pions have masses that are much smaller than the nucleons. So it's kind of, historically it just emerged as a consistent picture to view QCD as a spontaneously broken chiral symmetry. That's a good description at low energies.
So it's really just an interpretation to explain the pion in some way.
Yes, in some sense, I think it's just an interpretation because really everything is non-perturbative, and it's very, very hard to make like exact mathematical statements because you can't really calculate with QCD at low energies. But you can, you see this pattern of pions that fits exactly this symmetry breaking pattern, and then you can compare with lattice calculations, and you can if you make this assumption that QCD is described by a chiral Lagrangian, then you can make predictions. You can predict pion scattering, pion nucleon scattering, and you can predict particle ratios and so on, like ratios of the meson masses. And this all comes out in agreement with experiment. So this is a very well established picture. So we can really trust it, I think.
Okay, thanks a lot.
Okay, sure. More questions? I think at this stage it's very good if you just ask questions, because then I'm at least explaining what you want to know instead of just writing formulas. So feel free to interrupt anytime. In any case, let me just, as an example, write down a type of Lagrangian that we can write with this U field, and the leading Lagrangian that describes pions has the following form. It's just f squared, so this constant squared, divided by 4, and then it's the trace of the following d mu u d mu u. So u is this matrix that we defined here, and d mu is just the derivative. And I assume there should be a dagger somewhere here. And you see, one thing that you see, so this matrix is unitary, so you see that u dagger u is just 1. so there's no physics information in just the term u dagger u. So the first term that is non-zero, you need a derivative. Okay, and this essentially tells you that these gallstones or pions, their interactions always come with a momentum. Okay, that's a general feature of the chiral Lagrangian. Okay, so the leading term is already in some sense momentum suppressed. Let me continue for a few minutes and then we make a short break. What I wanted to show you, so I mentioned already before, this symmetry is not exact because there are quark mass terms in the Qcd Lagrangian. So let's go back to the quark picture and write the mass terms. And the mass term looks something like this, minus q bar, and then the mass matrix of the quarks, q. So mq is just m up, m down, m strange, diagonal matrix. And again, you can split this into left and right-handed fields. So equals minus q bar left, mq q right, minus q bar right, mq q left. And now you see this is not invariant. If I rotate, for example, only the left-handed fields, then there's nothing in the right-handed fields that compensates for this. So you see these mass terms, they break the chiral symmetry. This is only invariant if you rotate left and right-handed fields in the same way. Okay, so this breaks chiral symmetry. But now you can do an ingenious trick, and you say if mq scales as, under this rotation scales as, okay, let's say q right goes to, let's say v right, q right, q left goes to v left, q left. And then if you say, just arbitrarily, mq goes to v left dagger, or v left mq, v right dagger, then you see this term is actually invariant under chiral symmetry. Okay, if you just make this assumption. And now you can just do the same. Okay, so now we have this quark mass term. Okay, it's a mass term. And we say mq transforms like this. Okay, so now we can write down exactly the same term in the chiral Lagrangian with this M matrix that transforms like this. And this will be the equivalent of the quark mass term. And this will actually be the mass term for the pions. Okay, and if we do this, the Lagrangian looks like this. So we have the kinetic term for the pions, which contains also pion interactions. And now we write down a term which has exactly the same transformation property. And since it's a different term, it gets now a different constant that is just called B0 for some reason. And it looks like this, trace MQ U plus U dagger. So as an exercise, you can check that again, this term is invariant if you assume this is invariant under the chiral symmetry if you assume this transformation property of the mass matrix.
Could you remind me what
and
these
it
V's
turns
are?
out that this.
Sorry to interrupt. Are V's the matrices that diagonalize us in the mass basis? In the diagonal mass basis?
V and this VL and VR.
Mm-hmm.
These are just general SU3 matrices. Just because this, the Lagrangian has this SU3 cross SU3 symmetry, so I just denoted them by VL and VR. Then they don't diagonalize anything. They're just if the masses are zero, they just don't have any effect, let's say. What they do is they rotate up, down, and strange quarks into each other. So as long as the masses are 0, you can't distinguish them.
Got it. Okay, thank you.
Okay. Okay. I think if this goes now very fast, and I don't want to spend too much time now on the details, but this would be a topic for the discussion sessions. I would be very happy to explain this in more detail and to do examples or to answer any questions that you have, if there's interest. I want to make 2 comments. One is less important and one is very important. So the less important comment is, if you take this mass term here and you expand it out, so you take this exponential of the pion fields and you evaluate the trace and all this, there will be terms that look like something like this. There will be a mass term times terms quadratic in the pion fields, so something like this. So these are just mass terms for the pions, and from this you can read off that the pion masses are proportional to the pion masses squared are proportional to the quark masses. It just comes out of this piece. Okay, so that's just a side information in some sense. The important remark is that we can do the same trick as we did for the quark mass terms. We can do for the dark matter interactions, and that's the whole reason why I'm showing this. So if we have, so instead of a quark mass term that looks like this, Q bar MQQ, you can have terms that look like, I don't know, what did we have? The vector currents. So now you do the same thing. You ask the question, what is the kind of the formal transformation property of this dark matter current such that this whole thing is invariant under the chiral symmetry? And then you write down the analogous expression with the same dark matter current, but in terms of pion currents, in terms of pion fields. And that gives you just a dictionary how to translate from quarks to pions, or like from quark interactions with dark matter to pion interactions with dark matter. Okay, and again, I will just write down what we get for our 2 examples. And so there's some prefactor, and then we have a big trace, and then it looks like this, U, and then V dot D, U dagger, plus the Hermitian conjugate, and then times the dark matter interaction. So here it's our C16 in terms of our non-relativistic dark matter fields. So this V is essentially the V mu that came from the non-relativistic limit of the vector current, and it's contracted here with the derivatives that act on the pion fields. Okay, and then I want to show you the other example of the pseudoscalar exchange, and it looks like this. So we have a term, because we defined our pseudoscalar operators with quark mass field, so we have a quark mass matrix here also, and then because the leading term vanished, the dark matter current is just this derivative of the spin current. And these other factors just determined by the symmetry transformation properties of these dark matter currents in some sense. Plus it is, okay, you always write this Lagrangian such that it is Hermitian and that it is that it conserves parity, because Qcd conserves parity. Okay. we have about half an hour left, but I have the feeling maybe it's good to have like a 2-minute break at least to just relax for a moment, breathe fresh air, and then we continue. And as usual, I'll stay here. If you have questions, I can answer questions.
I have one about that very last part, which I think this might be kind of basic, but why does the mass matrix appear in the pseudoscalar case and not the other case?
Yeah, so that's just a convention, because remember, I'm not even sure I wrote it correctly above. Yeah, here. That's just how we defined our operator. So the vector operator we defined just as the product of the vector currents, whereas the pseudoscalar operator is just defined in terms with this MQ factor. We discussed this a little bit last time. It's just because in some models, or in many models, this factor comes out automatically, but it's just a convention in some sense. It has no deep significance by itself.
Okay, thank you.
It's just
Okay, so see you in 3 minutes, Joachim?
yes, sounds
Okay.
very good.
Okay.
Recording stopped. Recording in progress.
Okay, Joachim, please go ahead.
Okay, very good. Let's continue. Welcome back. Okay, so the discussion in the last, I don't know, 10, 15 minutes, it skipped many details. And I hope it became kind of clear, but let me maybe summarize again the main point here. And the main point is that we can't solve QCD at low energies analytically because it's non-perturbative. So one of our tools is just to use all symmetries that we have. Lorentz symmetry, parity, and in particular chiral symmetry, and the structure of chiral symmetry breaking that is very well understood experimentally. And now we just write down 2 Lagrangians that have exactly the same symmetry properties. One Lagrangian is in terms of quark fields, and the other Lagrangian is in terms of pion fields. And that's just a technical way of doing this that I tried to kind of sketch, and I was probably not very successful, but that's the underlying idea. We just write down 2 Lagrangians that have exactly the same symmetry. So we can be kind of confident that they're actually describing the same physics. Okay, and this is borne out just by experimental observations. If we use this Lagrangian, the pion Lagrangian, it agrees very well with experiment. And that's why we are confident that we can use it. And then we can extend this procedure to include dark matter interactions. Okay, and that's just the structure of the Lagrangian that comes out. Let me point out one more thing. Let's look at this Lagrangian. I mean, so one thing to point out is that there are very few constants. There's just this F constant and this B0 constant. So there are just 2 constants, but there are lots of pion fields and lots of different interactions. So you see that the symmetry relates many of these interactions. Okay, so that's kind of the simplification that we get from the symmetry, that we can describe interactions in terms of very few constants that we need to take from experiment. For example, this pion decay constant, this B constant you can calculate using lattice QCD. But once they're fixed, we have a full Lagrangian where everything is known and we can start making predictions. Okay, so that's kind of an essential idea. And then what you also see is well, what is not super obvious, but if you play a little bit with these U matrices, and I invite you to do this, it's one of the exercises. You see that if you expand these U matrices in terms of the pion fields, you see that this vector current that looks like this in the non-relativistic limit, it will always couple to at least 2 pions. Okay, so there's no. So the couplings, so in terms of Feynman diagrams, it will always look something like this. the dark matter and 2 pions. And it's okay, I'm just saying it, and I'll say more about this later. If you do the same exercise for the second term, for the pseudoscalar current, then you will see that this term, like this spin term, because there's all, you see here, this term is quadratic in the U field, so this essentially it gives you 2 pion fields, and this term is linear in the U field, so this gives you an interaction with a single pion. Okay, so it will give you something like this. Chi, pi, and here you have chi, and 2 pions. Okay, so just for the moment, keep this in mind. And now we need to, of course, discuss something else, because now we discuss all the time interactions with pions, but we are not, I mean, essentially, like, ultimately we are interested in scattering of chi dark matter particles on nucleons or on atomic nuclei. Okay, so why am I talking about pions? That was just to introduce this idea how this whole strategy works. And as you can imagine, there's a similar way of doing this for nucleons. It's just even slightly more complicated because we need to treat nucleons as non-relativistic fields. So we need to do the non-relativistic reduction of the nucleon fields. And then there's another kind of complication, or like something that makes it a bit more non-trivial, is that for the pion fields, it's kind of clear how they have to transform under chiral symmetry. For the nucleons, you have a lot of freedom. Okay, so what I want to do now is I don't give you any details, and I just write down the results, what we do.
Could I ask
and we can, yes.
Sorry, thank you. Could I ask a quick question about that last bit with the pions? It's not clear to me why we require coupling to 2 pions.
Yeah, I think the best way to see this is, I think you have to take this term and expand everything. So remember this U matrix is just is essentially the exponential of this pion matrix. So that goes like something like 1 plus pi plus terms that are quadratic in the pion matrix, something like this, up to factors. And then if you do this thing, I think it turns out that the leading, so the term with the 1, that just cancels, because they have probably forgot a factor of I, so there are probably factors of I here somewhere. The leading term cancels, and this 1 term and the pion term cancels, and the only thing that remains is the term that is quadratic in the pion fields. So you just need to do the calculation. It's not super hard. You just need to insert this expansion for the U matrix. Whereas here in the second one, you see just the daggers and the minus signs that just conspire in such a way that the leading term is the one with a single pion field.
Is there any physical intuition for what's going on there? I can see the mathematical argument, but.
Yeah, so I think the physical intuition, yeah, that's actually a good point. The physical intuition, I would say, is pions are pseudoscalar particles, so they're odd under parity. But we constructed this whole Lagrangian to conserve parity, or like at least the Qcd part. So since the vector current is even under parity, it couples to 2 pions, because 1 pion is a pseudoscalar, so it's odd under parity, but 2 pions can be even under parity. So that's how you see this. Here, for this, in the second case, we couple to a pseudoscalar current that reduced to a spin coupling in the low energy limit, and that's pseudoscalar, and the pion is a pseudoscalar, so this times a pion again is even under parity. So that's kind of the rule of thumb.
Okay, that helps. Thank you.
Yeah. So I don't, at the moment at least, I don't see how you see that the term with no pions vanishes, but at least, so yeah, that's the rule of thumb. Okay. So, yeah, that's the physics behind it. Excellent question. Thank you. All right. Nucleons. So what we do is we do something like we did for the dark matter field. We do for our matter fields, and we introduce an non-relativistic nucleon field or baryon field, B for baryon, but it's essentially just a nucleon. And this is defined, and I'm just writing the results as exponential of I mass of the nucleon V slash V dot X times B of X, where this is the relativistic nucleon field, and this exponential factor, again, it just scales out the mass out of the momentum, and it projects onto the the particle fields as opposed to antiparticle fields. And for our purposes, again, you can think of this as a 3x3 matrix, and since we are interested only in protons and neutrons, it has just this form, P, like a proton, a non-relativistic proton field, a non-relativistic neutron field, and otherwise zeros. Instead of the zeros, there would be, let's say, lambdas and sigmas and so on, like higher resonances, but we have not enough, or if we neglect these resonances, or if we assume there's not enough energy to excite these resonances, we can just set them to 0. So that's just a non-relativistic proton and nucleon field, proton and neutron field, excuse me. Okay, and then you go through this exercise. You think of how these baryon fields, how this matrix transforms under the chiral symmetry. There's a considerable freedom how to do this, but let's not get too concerned about these details. What you can do is you can use the same trick. You identify the symmetry transformation properties of these fields, the symmetry transformation properties of the dark matter currents. And then you translate products of dark matter currents times quark currents into nucleon currents. And what you get, I just write the result. What you get is something like this, for example. So this is called a heavy baryon chiral perturbation theory, long name. And it has terms in it that are of the following form. For example, for our vector current. So that's the kind of a non-relativistic reduction of our vector current, and then it couples to two protons, for example, to a proton current with a coefficient that depends on these Wilson coefficients of our interaction. So it's 2 times C hat 1U plus C hat 1D. Okay, that's if you go through all the math and all the complications, that's what comes out. But that's very nice because that's exactly what we got out before for the vector current from using baryon number conservation. So that's kind of built into this formalism, because as you see, in each proton there are 2 up quarks and 1 down quark, and that's exactly how the coefficient come out. You have a factor 2 here and a factor of 1 here. And if you want to couple to neutrons, you get exactly kind of the opposite. So the neutron interaction would look like this. And you would have 2C1D plus C1 up. Okay, so that's kind of nice that we reproduce our previous result. Okay, so that's the vector current. What about the pseudoscalar coupling that we had before? So again, if you go through the whole formalism, there's no coupling of a pseudoscalar current or a spin current to just 2 nucleons, to a proton or to a proton current or a neutron current. And again, the argument is the same as we discussed before, because these proton and neutron currents, they're CP even, and the nucleon current is CP odd. So there's no such coupling. The first coupling that you can have is a dark matter, let's say, with a spin, and 2 nucleons, and then you need a pion. Okay, so that's the first non-zero coupling. Okay, but there's there's another. So how do we couple the spin current to the nucleons? There's another way of doing this, and that's by recognizing that pions couple to nucleons. So if you just have pure QCD, like forget about dark matter, you have just the pure QCD theory, then there's a coupling between pions and nucleons, and it is of the following form. Yet another low energy constant, Ga, divided by our F that we know already, and then derivative of this nucleon spin current. So P bar V as mu PV minus N bar V as mu NV times pi 0. And this again, that's a constant that you can measure or calculate. It's just a number for our purposes. Okay. So let's summarize all these ingredients. So let's say we want to calculate the scattering of dark matter on a nucleus with a vector interactions, so vector. So that just gives us our Feynman diagram that we had before. Okay, so we have chi coming in, chi going out, and it scatters on a nucleus. And we saw that we actually can coherently sum over all these nucleons, so we can just scatter on the atomic nucleus. For the pseudoscalar current, so how do we scatter via pseudoscalar current? So the leading interaction is the following. So we have seen the dark matter, for if this is a pseudoscalar current, it can emit a pion. Yeah, that's this dark matter pion interaction, and this pion can be absorbed by the nucleons. Okay, so that's actually how a dark matter interacts with a dark matter with a pseudoscalar coupling, or dark matter with a pseudoscalar mediator interacts with nucleons via exchange of pions. That comes out of the formalism. It's not a contact interaction like this, but it's an interaction via exchange of pions. Okay, so that's why we need to know the interactions of dark matter not only with nuclei but also with pions. Okay, that's the leading interaction.
I have a question.
Yes.
Thanks. It's surprising to me that we didn't include any shielding effects anywhere in here. Are those only valid at higher energies?
Okay, so could you repeat the question? I had a hard time hearing it.
Oh yeah, sorry about that. It's surprising to me that we didn't include any shielding effects in here anywhere. Are those only valid at higher energies?
I'm not sure what you mean by shielding effect, but it is true that these interactions with pions, they come with a derivative. So both the interaction here and the interaction here comes with a derivative. So this one was completely independent of any derivatives. That was just a contact interaction 1 over m to the 4. Here, that goes like, so you get the momentum here. Let's say here you get a momentum. Here you get a momentum in this interaction. So that goes something like q squared. And then you have the pion propagator. That goes something like q squared minus m pion squared. So I don't know, you might call this a shielding. For sure this is a momentum dependent interaction. So it depends on energy. It depends on the momentum transfer. So if you have an experiment that is sensitive to a certain range of momentum transfer, you need to integrate over this momentum window, and you have to take this factor into account.
Sorry, my question wasn't clear. I meant shielding in heavy atoms from the electrons, from the valence electrons.
Are you asking about scattering on the electrons?
Yes, or like effects of the valence electrons in these heavy atoms.
Yeah, I'm not 100% sure what the question is, but this I neglected all effects of electrons at the moment. I just assumed that dark matter couples to quarks. If it couples also to electrons, then it might scatter on the electrons, but that's kind of a different formalism. So for the sake of the discussion here, I think you can neglect these effects.
Okay, that makes sense. Thank you.
In some sense, or we neglected them for sure. I think that they play a bigger role if dark matter gets very light. If dark matter is heavy enough, I think the dominant contribution comes from scattering on nuclei, just from the kinematics, I would say. Okay. So now we have 5 minutes left. So I'm gonna skip some discussion. What I wanted to discuss is like how to identify which interactions are the leading ones and which ones are the non-leading ones, and how to say more about this and how to make sense of all these non-perturbative pion exchanges. But I'm just skipping all this, and if you're interested, we can discuss this in the discussion session tomorrow. And instead, let me just make the connection to something that you have seen before in these lectures, and that is usually called the dark matter effective theory. And that's kind of where we arrived after these many steps. So after these many steps of going to non-relativistic limits and of going from quarks to nucleons, our interactions now look something like this. So for the vector current, we have seen that we have just a contact interaction. So we can write this in terms of nucleon fields as an operator that looks like this. It's just a unit interaction, or like how do you say? It's contact interaction on dark matter times a contact interaction on nucleons. It's just some kind of convention how to write these operators. We can also, really you should write them as chi v times nucleon, non-relativistic times nucleon. Just the convention is to just drop these fields and just keep the matrix that's in between here, which is just a unit matrix in this sense. It's kind of a conventional notation. I don't know why it's chosen like this. So that's what corresponds to our Q1, Q6 operator in the non-relativistic limit. It reduces to this one. Whereas our pseudoscalar exchange, I think it was 8, 7, reduces to a different operator in terms of nucleon fields. And we have seen that we have a spin interaction in the dark matter sector and a spin interaction in the nucleon sector. So the corresponding operator in this case is called 06N, and this is written as dark matter spin dot Q divided by M chi. So that's the dark matter spin interaction, and we have seen it comes with a momentum. And then similar for the nucleon side, nucleon spin dot Q over M nucleon. So I think you have seen these operators before. There are also other operators. There's, for example, O4, which would be just this times, like the nucleon spin times the dark matter spin, and so on. There are more of these operators. But what you have seen is these operators naturally arise if you start with an interaction at high energies, like a model of dark matter, and then you do all these approximations that we did. You end up with these operators. And the coefficients of these operators are just given, you can calculate them. So in this case, for this ON1 operator, our vector current, it was just GV prime divided by M to the MV squared. Okay, so that's kind of, you see the dark matter effective theory is just not one effective theory, it's a whole set of effective theories, like with operators and interactions that are appropriate for the description of the physics. So if you want to write down a dark matter model, you typically write the dark matter model in terms of quark fields and lepton fields and dark matter fields and maybe gluons and photons, dipole interaction, something like this. But this description is not necessarily the most useful if you want to calculate scattering. So you go to all these steps, going to the non-relativistic limit, going to the pion and nucleon picture, and so on. And you end up with these nuclear operators. And the coefficients of these nuclear operators you can just calculate. Okay, so dark matter effective theory is just really a whole tower of effective theories that are all connected. And in the last minute, let me just say that once we know the coefficients of these operators, what we need to do is we need the matrix element of these operators in the nucleus. And this has been calculated using a shell model for a whole bunch of different nuclei that are used in direct detection. And that's this Fitzpatrick and Haxton and et al. Paper. And they give a formula for the cross-section, so the differential cross-section differential in the energy transfer. And I will just write it down. It's just mass of the nucleus, so that's just a normalization divided by 2 pi v squared, where v is the dark matter velocity. And then it's a sum over all these operators, or rather over all these matrix elements of these operators for both protons and neutrons, and you sum over all these types of operators. So there's a sum over ij, and then sum over n primed, which can be protons and neutrons, sorry. And they come with coefficients Ci, n, Cj, n primed, and then form factors or matrix elements of these operators inside the nucleus. And they are given just numerically in the paper that is cited in the lecture notes. So these are just functions of the momentum transfer. And once you have these functions, and in the lecture we have learned how to calculate these coefficients using this tower of effective theories, you have solved the problem, let's say, in a very general way. You can start with like a very general interaction in the UV. You go through the steps that I showed you. You end up with these coefficients. And then in this paper, or like in this paper or in any equivalent paper where people calculate this matrix element, you get the matrix elements and form factors of these operators. And this gives you the cross section. So that's kind of the general result. And maybe last comment before I conclude is that, as I said before, there's no need to do these calculations by yourself because there's computer code that does it. And essentially there are 2 programs. One program is called DirectDM. And again, the citations and the links are in the lecture notes. And this one gives you the step going from the UV to the non-relativistic coefficients. So you can just specify a model. You say which operators are present, and it calculates these non-relativistic coefficients, taking into account all the approximations, pion interactions, and so on, everything. And then once you have these non-relativistic coefficients, there's another program called DM form factor. And it takes output of DirectDM, and it gives you the cross-section. So from the CN, from these non-relativistic coefficients, it gives you the differential cross-section. And then you can integrate this over the sensitivity range of your chosen experiment with the chosen nucleus, and it gives you the scattering rate. And then this gives you the comparison between experiment and theory. Okay, so that was super quick summary, but let me stop here and see if there are any more questions.
I don't see any here, nor on Zoom. So thank you very much, Joachim, and see you next time, tomorrow, same time. Thank you.
Thank you very much.
Okay, thanks.
Recording stopped.